So this video lecture is a continuation of the rate law expression video. We are picking up with problem number 2, which says that the following data was obtained for this chemical reaction A plus B turning into products. We have 3 trials. We have the initial concentration of A in moles per liter. We have the initial concentration of B in moles per liter, and we have the initial rate of formation of the products in moles per liters per second. So again, we're looking for the rate law expression for the reaction, we're looking to determine the rate constant, and we are looking to find the overall reaction order. So in all of these, when you're determining the rate law expression, you are basically starting the same place. It's a generic equation to begin with. You start by writing rate is equal to the rate constant K times the concentration of your first reactant, in this case it's A, times the concentration of your other reactant, in this case it's B, and now our job is to figure out the exponents, the magnitude of the order on both A and B. And so to do those, to find those exponents, we're going to have to look at our data, our experimental data. All right, so if we take a look at reactant A, we want to find 2 trials where A is constant. So you can see here that in trials 3 and trials 1, the concentration of A is constant. So now we can focus and see what the effect of B has on our rate of reaction. So here, if we look at from trial 3 to trial 1, they don't have to be in order, but we can see here that trial 1, we have twice the concentration, right? If we go in this direction, we've doubled the concentration of B. So I'm going to do a little scratch work over here. So this is for reactant B. Right? If I double B from 3 to 6, what is the resulting effect on the rate? Well, here you can see here that 1.6 divided by 0.4 is going to give you a rate increase of 4 times. So what do I need here? I'm going to use the letter M here. What power of M do I need to raise the doubling to in order to get the increase in the reaction rate to be 4 times? Well, 2 squared is going to equal 4. So that means the exponent that I'm going to put on the reactant B is going to be a square, a 2. Okay? So now let's take a look at reactant A. To see the effect of reactant A, we have to find 2 trials where reactant B is constant. Okay, so here I see trials 1 and 2 where B is constant. So let's take a look and see what's going on with A and how it affects the overall rate. So here, if I go from trial 2 up to trial 1, I see that there is a doubling happening from 2 to 4. That's a doubling. What is the resulting effect on the reaction rate? Well, from 8 up to 1.6, or if you want to think about it by dividing the bigger number by the smaller number, 1.6 divided by 8 is also a doubling. So the exponent I need to put here on the initial change in concentration of A is going to have to be equal to 1. So what we have found here is by looking at the experimental data, we found that the reaction order for reactant A is the first order, and the reaction order for reactant B is second order. So if we were to go ahead and jump to answer part C, this is a simple question. The overall reaction order is you just take the sum of the exponents. So 1 plus 2, this is what we say is overall third order. Okay, well, let's go back to part B. Part B is a little bit trickier because we need to solve for the rate constant. Okay, so we're going to rearrange this rate law expression here. And if we rearrange that for the rate constant K, we're going to get the rate divided by the concentration of A to the first power times the concentration of B to the second power. Right? And now we just have to go pick a trial. It doesn't matter which trial you choose, just pick a trial and substitute in the rate, the concentration of A and the concentration of B, and solve for K. So I tend to choose trial 1. I don't know, it just seems to make sense to me to pick the first one. So the initial rate of formation is 1.60, and that unit was moles per liters per second. I believe, yes, seconds? Yes. And we're going to divide that by, let's see, the A for trial 1 was 4.0, that is moles per liter. That's to the first power. Then we're going to take the concentration of B, which was a 6.0 moles per liter, but that has got to be squared. Okay, so let's see what happens. Moles will cancel, liters will cancel, but let's take a look and see how this all sorts itself out. So if we rearrange this, we're going to get 1.601 over seconds. And then we are going to get 6 squared is 36 times 4 is 144. So the numbers sort out to 144. We don't actually want to reduce that number down in terms of significant figures because it's an intermediate number. But we're going to see that it's going to have a mole squared divided by liter squared. And when we sort out 1.60 divided by 144, here's where we're going to limit us to 2 significant figures. And we'll have 0.011. When we sort out our units, we're going to end up with liters squared over moles squared times seconds, right? So that's going to be our rate constant for that particular reaction. All right, let's take a look at our next problem, number 3. All right, number 3. We have, again, another chemical reaction, A plus B turning into products. We have 3 trials. We have an initial concentration of A, initial concentration of B, both in moles per liters. We have an initial rate of formation of products in moles per liters per second. It's going to start out the same way. This problem's going to have a little twist. Number 1, we're going to determine the rate law for this reaction. We're going to then find the rate constant, and then we're going to figure out the initial rate of reaction when we have a new set of conditions. So we're going to start off this problem the same way, right? What have we been doing? We've been starting by writing the generic rate law expression. The rate is equal to K. Okay, we still have our reactants A times the concentrations of A times the concentration of B. That part's the same. We just need to figure out what those exponents are going to be before we move on and finalize that rate law expression. So let's find in our data table 2 trials for reactant A, where let's say where A is the constant one. We'll do that one first. So where A is constant, so I see trials 2 and trials 3 where A is constant. What's happening with B? Okay, so if I go, let's start with a smaller amount of B up to the larger amount of B, 0.020 up to 0.040, that is a doubling. Okay, so if A is constant, right, what's happening with B? If we double B, what's the effect on the rate? Okay, well, these numbers are kind of goofy. They're kind of hard to see. But if you take the larger number and divide it by the smaller number, all right, we can see that when you take 1.92 times 10 to the negative 5th and divide it by 9.6 times 10 to the negative 6, you can, your calculator will tell you that the larger number is increased, or it's twice as large. So what we need to do here is figure out if you double B, that's what we said here with this 2, what's the effect on the rate? Well, the rate was also doubled, which means that our exponent here, whoops, move that. Sorry about that. Our exponent, our order for that for B, because that was the effect of B, is going to be first order. Okay, so now we need to do this again where B is constant. What's happening with A? So let's go back and look at our data table. What we see where B is constant, that's going to be trials 1 and 2. What's happening here from trial 1 to trial 2? We see a doubling of A. So a doubling of A, what's that effect on the rate? Well, okay, from 9.6 times 10 to the negative 6 up to 1.92 times 10 to the negative 5. That is also, the rate will double. So again, this is first order for the reactant A as well. So what we see here is our rate law expression for this particular equation. So rearranging for the rate law constant, we get the rate over the concentration of A times the concentration of B. Now we need to just substitute in the information from one of the trials. Again, we're going to pick trial number 1, where the rate was 9.6 times 10 to the negative 6. That was moles per liters times second. In trial 1, the concentration of A was 0.040 moles per liter. The concentration of B was also 0.040 moles per liter. Okay, and let's see what happens when we start canceling out units. Moles will cancel, liters will cancel, and when we sort of reduce this down, scroll that down a little bit, we're going to get 9.6 times 10 to the negative 6. That's going to be 1 over seconds in the numerator. In the denominator, we're going to have 0.0016 moles per liter. And when we reduce that down even further, we're going to find that K is going to be equal to 0.0060, and our unit will work out to liters over moles times seconds. So here we're seeing that the unit is definitely different because we just had an overall reaction order of it was second order, it wasn't third order like in the first couple of examples. All right, well now in part C of this, what we now need to do, whoops, hold on there. What we now need to do is to discover the initial rate of reaction when we have an initial concentration of A to be 0.12 moles per liter and an initial concentration of B to be 0.015 moles per liter. So this is where we go back to the original rate law expression, which was rate is equal to K times A times B. Those exponents were both 1s in this case. And now we substitute in these new concentrations, but since we know K, that's going to go in that spot. So here's how we can figure out this new rate with these new concentrations. So we're going to have 0.0060. The unit is liters over moles times seconds. That's just the rate law constant. Here, our initial concentration of A is 0.12 moles per liter, and the initial concentration of B was 0.015 moles per liter. All right, and so what will happen in terms of units canceling, that liters will cancel, that moles will cancel, and we will have the unit of moles per liters per second, which is just a perfectly fine rate unit. It's the concentration per second. And what you will see then is that your calculator gives you a number 1.08. We're going to reduce that down to 1.1 to reflect the correct number of significant figures. So this is going to be 1.1 times 10 to the negative 5th moles per liter per second, and that's going to be the new rate at those new set of initial conditions. All right, we're going to continue this on in a third video lecture so we can show you how the fourth and the fifth problems can be done, and we'll see you back in the classroom.